Hello. I welcome you to the fourth episode of the Itihas podcast. I am Arnapati, and you are listening to how the Earth has been evolving so far. In the last few episodes, we spoke about the Proterozoic Aeon. We saw that this Proterozoic Aeon, it spans almost half of Earth's history from 2.5 billion to about 542 million years ago, which is a long, very long time. This is about 40% of the Earth's lifespan, right? So, and in that, we saw that in the very first 500 million years or so, there was this great flourishing of photosynthetic algae and the consequent rise of atmospheric oxygen, the transformation of once iron-rich oceans by the deposition of these massive banded iron formations, and the biological innovation of eukaryotic cells with their DNA sequestered in a nucleus. And as we know, that these cells will go on to become the precursors of plants and animals that we see today. Now, that was the early 500 million years, right? And after that, as we spoke in the last episode, we saw what we consider the boring billion, or the time period where not a lot of things are happening. Yet, as we did discover, there were a lot of these deconstruction of big cratons happening, and we were encountering a lot of these supercontinents, be it Ur, Kenorland, Columbia or Nuna, and then finally we stopped at Rodinia. Now, if you contrast that, the final 300 million years or so are going to be very dynamic, with continental breakup and assembly, radical climate swings, epic shifts in the ocean and atmospheric chemistry, and the rise of animal life. And in all of this, I hope you've understood that everything, most of the systems in Earth, be it its air, water, land, they all appear to be quite interconnected. They're not very separate spheres. It's just that the change in each of them happens at a varied length of time. Weather varies daily, oceans change over millennia, rock cycles over millions of years, and these supercontinents take hundreds of millions of years to assemble and break apart. And yet, every Earth system affects every other in both ways that are obvious and hidden from our point of view. Now, as we move forward with our discussions about these Earth systems, one thing that will become very common in our discussions would be the presence of positive and negative feedback loops. Now, let's take a step back. Let's move a little away from how Earth functions and just talk about positive and negative feedback loops in our daily lives. Let's take the example of a kid. A kid likes eating candy. They crave candy, and whenever they crave candy, they would either ask for it, and if they have grown up a little bit, like you and me, they would go ahead and buy something for themselves, which is nice and sweet and really satisfies their craving. Now here, the craving is what is requiring you to go and buy it. So more the craving, more you buy it, more you like it, more you buy it. So it's a very good, easy example of a positive feedback loop. You are wanting, you want to have sweets, you go buy sweets. Now, at the same time, you would have heard this at some point in your life where you shouldn't eat a lot of sweets. Either it could be your parents, your teachers, or at this point, maybe your significant other reprimanding you from having sweets. Now, that would be a negative feedback loop, because them reprimanding you would make you feel guilty, or in fact, you yourself might just feel guilty after having a few bites of those delicious ice creams that are there in your freezer. So at that point, you would not want to have more. So if that can be considered as a negative feedback loop, then I mean, you can at this point guess that a lot of things in our lives work on negative feedback loops. And I'm not only talking about us humans, I'm also talking about non-living things. For example, just look at your toilet flush. Yeah, you flush the toilet, the water starts filling up, there is a valve there, there's a floater there that's connected to the valve. As the water fills up, it brings that floater up, it closes the valve, and there you go. The water is not being poured inside that flush anymore. So that, again, it's a negative feedback loop. Now, the reason why we are talking about these positive and negative feedback loops is because the Earth as a system also works on these big positive and negative feedback loops. For example, if you take the warming of oceans, as the oceans warms up, it produces more moisture because more water is getting evaporated. That moisture goes up and becomes clouds. Clouds themselves tend to reflect more sunlight. because the albedo is high. We'll talk about albedo as we go forward with this, but yeah, the clouds do reflect more sunlight, so that way less sunlight is reaching the water or the oceans below, and less water is getting evaporated, and consequently the ocean will cool down. So that itself is a negative feedback loop. Similarly, if you look at rising concentration of atmospheric carbon dioxide, it'll cause global warming. As global warming happens, as temperatures rise up, they will produce more weathering in terms of, let's say, rising sea levels will erode more rocks, and more rocks getting eroded would expose materials like magnesiums and calciums, which will then react with the carbon dioxide, sequestering that carbon dioxide away and reducing the amount of carbon dioxide present, which is again a negative feedback loop. And then at the same time, this can produce a positive feedback loop. For example, a warming ocean might cause the widespread melting of methane-rich ice at and beneath the ocean floor, which could add the greenhouse gas methane to the atmosphere and cause even more warming, which would release even more methane, and this cycle would continue. So you can already see that both positive and negative feedback loops are intrinsically tied to how the Earth reacts at a given point of time. Now, this boring billion that we talk about, to the extent that it really was boring, was a consequence of many efficient negative feedback loops that held very extreme changes in check. Earth's climate seems to have been fairly stable during this time. There was no great ice ages, the chemistry of the anoxic, sulfur-rich ocean did not really change much, nor did the life evolve in any striking way. There were some new minerals that were added, but there were no major tipping points altering the air, land, and sea. But all of that was going to change. All of that was going to change with the breakup of Rodinia. Now, if you would remember, Rodinia is where we left off, right? At 850 million years ago. And if you would recall, Rodinia was this huge landmass which was majorly around the equator, but also spanning a little more towards the north and south. And this huge chunk of landmass was so big that most of its inner area was just barren land, because not a lot of moisture would reach in from the oceans around it, which was the Merovia Ocean. So not a lot was happening in Rodinia. And at this point, I would love to introduce this particular thought exercise that I usually do with my students, where I ask them that if I were to give you a time machine right now, what would it take you to go ahead and survive at a particular time period? So let's say if I were to go back at this particular time period in Rodinia, which is 850 million years ago, what would it take for me to survive? And I would say at this point, maybe a big tank full of oxygen and a very, very good sunscreen with some really, really good snacks. And I might be able to survive in Rodinia, say, for a day or a week or so. And the reason why this thought experiment becomes more important for us is because we try to see at what point the Earth becomes completely livable, habitable, the way it is today. Now, coming back to our Rodinia at hand, I also want you to recall this particular thing that we had mentioned during our previous podcast, where I told you that whenever we talk about cutoff dates in the geological timescale, whenever we say particular time periods existed from this point to that point, for example, the boring billion, it existed from 1.8 billion years ago till 850 billion years ago. So are these numbers arbitrary? No, they're not. The fact that we're talking about 850 million years ago in particular is because at this point onwards, something big happens. We see that the first rift happens around this time period, which was at the Congo and Kalahari cratons, which at this point began to separate to the southwest of the otherwise intact Rodinia supercontinent. Then about 800 million years ago, a second small rift zone isolated the West African craton, which moved south from the main landmass. So you have one landmass moving towards southwest, the other one which is starting to move towards south. 50 more millions into it, we see that the Rodinia's fragmentation was in full swing, and by 750 million years ago, we see an extensive chain of volcanoes and basaltic lava flows reveal major cracks in the crust. And this is where the supercontinent split in half, as the great north-south rift zone separated the Ur to the west and a continental cluster of Laurentia, Baltica, and Amazonia, and the smaller craton towards the east. And these rifts are very, very important for us because this is what makes the non-boring period so non-boring. Because as we had spoken about in the previous podcast, the reason why this huge chunk of supercontinent was so boring because there was not a lot of sedimentation happening. There was not a lot of erosion happening because it was just one huge coastline which was interacting with the water, and there were no inland seas and there were no sedimentations in that sort of way happening. But the moment this rift happens, you would see that the dynamic sedimentary basins formed in the intercratonic seas and marked an end to the long hiatus in the Earth's rock record. That virtual cessation of sedimentary rock deposition that had begun in the Mesoproterozoic era and lasted for almost 250 million years is now coming to an end. And at the same time, you would see that the microbial life started flourishing in this shifting, fragmenting world. Eroded lands contributed mineral nutrients to these photosynthetic algae, which had long been limited by the ocean's meager store of phosphate, molybdenum, manganese, and other essential elements. And I hope you understand that the reason why all of this is happening is because new material is getting exposed to weathering. And with these upcoming tectonic activities, we would find that there are going to be huge alterations coming up on Earth's oceans, atmosphere, and climate. And while we discuss about these big changes, let's keep our previous discussion on negative and positive feedback loops in the back of our head so that we can sort of start judging every single one of these changes happening based on those feedback loops that we spoke about. Now, if you would recall, we had already spoken about how slowly the level of atmospheric oxygen was increasing because of the amount of algal bloom that was happening. Those small cyanobacteria slowly starting to consume a lot of the carbon dioxide and producing oxygen in return. But at the same time, this would mean that the organic carbon is now being consumed. Now, throughout Earth's history, we know that carbon-rich biomass like you and me, we have been the major consumers of oxygen. Now, by the same token, the faster carbon-rich biomass is buried, the faster the oxygen level rises. But how do we know that? How do we get to know that such biomass is being buried, or where is this consumption happening? And this is where things get so much more interesting, because we've found certain type of limestones that existed during this time period which have a very amazing carbon footprint on it. So limestones are basically calcium carbonates, right? Now, carbon isotopes in limestone point to a change in the production rate of algae. And what is this? Basically, see, what scientists have found is that life's most essential chemical reaction, which is the reaction of photosynthesis, where the conversion of water and carbon dioxide into sugar happens. During this process, the carbon that is being consumed is the isotopically lighter carbon, carbon-12, relative to carbon-13, which is the heavier counterpart. So, what this means is, during normal times, when the microbial life flourishes and light carbon is depleted from oceans, limestone displays a correspondingly heavy isotopic signature. Now, let's put this into the perspective of the positive feedback loop that we were talking about. So here, in our case, when Rodinia starts to break up, we see more sedimentation happening, and as more sedimentation starts to happen, more of these life-giving essential elements and minerals are coming into play, and because of that, more algal bloom is happening. Because more algal bloom is happening, more consumption of the lighter carbon is happening through the process of photosynthesis, and we are being left with limestones, which has a heavier carbon deposition, the heavier isotopic signature in it, which is the carbon-13. And sure enough, limestone deposits along the shore of Rodinia from 790 to 740 million years ago is unusually heavy. During that interval, algae must have spread and been buried at an unprecedented rate. And this is a positive feedback loop. More carbon dioxide is being consumed, more oxygen is being taken out. Now, let's not also forget the fact that as Rodinia starts to break up, the more and more volcanoes are coming in, because a lot of these tectonic activities are happening, and more these volcanoes are pushing out carbon dioxide from the surface towards the atmosphere, and the presence of carbon dioxide in the atmosphere will increase the amount of carbon dioxide available, and these algal blooms will keep on going and flourishing to a point where they keep on consuming and growing on this carbon dioxide that is being available. So again, this positive feedback loop is happening, and it is quite certainly now starting to affect the atmosphere of the Earth that is present here during this time period. Now, at the same time, there is another feedback loop that starts, which is the rifting of Rodinia resulted in thousands of miles of new seafloor volcanoes, which manufactured hot and lower density ocean crusts. Now, we will talk about oceanic crust and continental crusts a little more as we go forward, but for the time being, just look at how the breakup of Rodinia is resulting into the formation of a lot of inland seas, and these inland seas mean more evaporation and increased rainfall, which leads to more rapid weathering of exposed rock. And as more exposed rock is being weathered, more of those vital minerals are getting out, and more of these algal blooms will start happening. So we know that all of this will slowly, this big positive feedback loop will slowly go towards lowering the CO2 levels and in turn towards global cooling. And then at the same time, there's another system that was in play right before Rodinia started to break up. We know that land and oceans have different albedos, or the different rates at which they absorb and reflect back sunlight. Now, the albedo of oceans is a lot lower. They don't intend to radiate more heat than they absorb, whereas barren land would tend to do that more. So we know that the albedo of land is a lot higher. Now, when Rodinia was a complete big land mass, most of it was concentrated around equator, where we know the incident sunlight is a lot higher than it would be at poles. So consequently, because of that very reason, we know that the Rodinia was radiating a lot of heat during that time, which was helping maintain the global temperature. But as Rodinia started to break up and a lot of these rifts were forming, a lot of these inland seas were coming up, a lot of this heat that was being reflected from Rodinia would also decrease. And debates are still going on towards how much this would have affected, but it is clear that it would have had some sort of an effect towards the global cooling. Now, as we've set the stage with our whole idea of positive and negative feedback loops and towards the global cooling of Earth, it's time for us to finally see how the Earth's very first ice age happens. And this is not a normal ice age. Let me remind you, this is the harshest ice age the Earth will ever see. Because during this time, the Earth did not only experience an ice age, it was completely frozen over. See, when we talk about glaciation, right, there are certain telltale signs that we get to see when we talk about when and where glaciers were formed. There is something known as stellates. These are basically sediments left behind ice sheets when they move. They collect a lot of these sedimentations as they move, and the way these sedimentations are then later on studied by field geologists tells us where and how and during what time period this glaciation would have happened. Similar thing happens with moraines and warped, which are again specific features of glacial remains. Now, during 1998, Paul Hoffman and 3 of his colleagues, they produced a paper called A Neo-Proterozoic Snowball Earth. And the claims they made on that paper was quite outlandish for its time, because Hoffman and his co-workers, they made this extraordinary leap that at least twice during that interval, the interval from 740 to 580 million years ago, Earth had not just experienced an ice age but had completely frozen over from poles to equator. Now, the reason why this is very, very surprising is because we know from the most recent ice ages, even during that time period, the ice never reached below 45-degree latitude. And fossil evidences points to a relatively warm tropical zone even during that maximum extent of ice. Whereas Paul claimed that during this particular time period when the Earth was being frozen over, the observations they made from the glacial tillate and comparing it side by side with the paleomagnetic signals of the rocks found during this time period, they saw that the glaciers must have been as close to the equator as 12 degrees latitude, which basically means the Earth was completely frozen over. And this really is a mind-blowing discovery, because this sort of coincided with what we were talking about in terms of light and heavy carbon isotopes. we know that right before something like this would have happened, the eukaryotic cells being produced en masse was consuming carbon dioxide and producing a lot of oxygen. The carbon dioxide they were consuming was the lighter carbon, and hence the limestone deposits that we find during this time period were heavier in nature with the heavier carbon-13 isotope. So technically, if the Earth is being frozen over, during this time period, the limestone deposits that we should find should be relatively more balanced because most of the algal bloom would have died. Most of the eukaryotic cells which was doing the photosynthesis would have completely frozen over. So this should have coincided, and that's exactly what we find. We find that a huge decrease of more than 1% in heavy carbon just before and just after the appearance of glacial deposits about 700 million years ago happens. So here is the full story. We know that the Earth was cooling because of a lot of these positive feedback loops happening. One feedback depended on continental weathering, a process that accelerated in hot and humid tropical zones as it pulled more and more carbon dioxide from the air, because we know that more and more sediments were being exposed and they were pulling the carbon dioxide from the air. Now the second feedback loop that clicked was the massive blooms of photosynthetic algae which scavenged even more CO2 out of the air. Now, meanwhile these were happening, what would have happened is Earth's temperature would have started to go down and the poles would start to freeze. As the poles started to freeze and ice caps began to grow, they started reflecting more and more sunlight away. Because we know that the snow caps have a much higher albedo than anything. So at that point, instead of absorbing the heat from the sun, we were reflecting it away. So as more and more the sunlight started getting reflected away, the more cooling happened, and because all of these was just playing into one another, we would have these poles starting to freeze from the poles towards the equator to a point where slowly the whole encasing would have happened and Earth would have turned into a hard snowball. And Hoffman's paper points out that average temperature during this time period would have been somewhere close to minus 50 degrees Fahrenheit or minus 45 degrees Celsius, which is pretty cold. So what happens next? Because at this point, the whole Earth is encased into a mile-thick sheet of ice, being completely unable to soak up any solar radiation. The global ice age would have practically shut down any and almost every ecosystem that we were talking about. The whole abundant microbial life form would have been completely wiped out, and a few hardy microbes would have persisted in the hydrothermal vents deep inside the oceans, but that's about it. And maybe there would have been a very few photosynthetic algae which would have found some sort of sunlight through cracks that were being formed by either volcanoes or some sort of melting. So all in all, things look pretty grim for Earth. But here we are, you and me, listening to the Itihas podcast being produced by me, Arnapati, which means that at some point something would have gone right. At some point, the Earth would have thawed up. Now, you and I have solved the mystery of how the Snowball Earth happened. There was a lot of talk about these positive and negative feedback loops, and we are going to go back to that. Now, one of the things that really did not stop even during this time period was our planet's much deeper, inexorable churning that was happening. We're talking about the plate tectonics. The white veneer of ice and snow could not stop these plate tectonics, nor could it slow the incessant exhalation of the volcanic gases that were coming from these hundreds and thousands of black cones that were poking out of the ice. These volcanic eruptions that were happening, they were continuously pumping carbon dioxide into the atmosphere. Now, talking back about the same positive feedback loop, there was nothing to consume this carbon dioxide anymore, right? So more and more carbon dioxide was being pumped out, which slowly started increasing the amount of carbon dioxide present in the atmosphere, hence creating a runway for the new greenhouse effect to take place. So this basically meant that the sunlight which was still being scattered off the white icy landscape was now getting reflected by the carbon dioxide present in the atmosphere, and that radiation energy that was being bounced off right back to the surface inevitably started warming the planet. And let's not forget that this particular process is happening over many millions of years. As the atmosphere warmed, small patches of equatorial ice melted. As the dark land became exposed, more sunlight was absorbed and the warming accelerated. The ocean too began to clear their white coverings as this whole positive feedback loop between the sun and the surface caused the earth to become warmer and warmer. Now here I would also like to make an honorable mention of another particular feedback loop which is caused by the notorious methane gas, because We know, molecule for molecule, methane is a much more effective greenhouse gas compared to carbon dioxide, and methane for billions of years has been accumulating in the ocean floor sediments, probably by two mechanisms. One could be the involvement of microbes that release methane as part of their normal metabolic cycle, and the other one is the formation of methane during a tectonic movement. And this particular tectonic movement is still under debates and how that happens, because it basically involves the reaction of water and calcites alongside heavy temperatures and pressures. But all in all, we know that methane that is there, present and stored in the ocean floor, could have appeared and disappeared with the warming and cooling of the Earth itself. So coming back to our post-Snowball Earth, we know that the Earth is now starting to warm up, and we are slowly reaching the point where high amount of carbon dioxide is present in the atmosphere, and possibly there's a higher concentration of methane as well, due to which slowly the Snowball Earth is now transforming into a hothouse with the temperatures soaring to record levels. Now, for a long time, perhaps 30 million years, a warm climate prevailed, but the hothouse ensured its own demise. The elevated atmospheric concentration of carbon dioxide gradually fell from their extremes. Some of the greenhouse gas was removed by reaction with the rocks. The denuded land exposed to rainfall laced with the corrosive carbonic acid, because we know that the concentration of carbon dioxide is so high in the atmosphere, the rain falling would have created carbonic acid, which would have weathered the most of the land very, very rapidly. And then this weathering would have increased the amount of nutrients available, and then given that the sunshine is falling very gracefully on the oceans, this would have led to the resurgence of the explosive algal blooms, which would now start to absorb the greenhouse gases, the carbon dioxide again. And so for the next 150 million years, Earth cycled between these extremes. Not once, not twice, but at least 3 times. The ice gathered and retreated, the global climate swinging drunkenly from the Arctic to tropical and back again. The first episode, called the Strussian glaciation, reached a maximum about 720 million years ago. The Marinoian glaciation followed at 650 million years, and the less severe gaseous glaciation occurred at 580 million years. And so we finally reached the point where the hothouse algal blooms, aided by phosphorus and other nutrients which were being broken down with the whole weathering process, undoubtedly contributed to the sharp spikes in the atmospheric oxygen. And so, by about 650 million years ago, atmospheric oxygen had risen to near modern levels. And this is significant for us because we know that elevated oxygen has been implicated in the rise of complex multicellular life. For only with such high levels of oxygen could organisms adopt the active, energy-demanding lifestyle of, say, a jellyfish or worms. And indeed, the earliest known multicellular organisms appear in the fossil records about 630 million years ago, just after the second global snowball glaciation happens. Now, to understand the rise of animal life in the Neo-Proterozoic era, we must first look further back more than a billion years to just before the Boring Billion. And that is something we'll talk about in the next episode when we start looking at complex life forms. But at least we have finally answered the question of the Snowball Earth. But this was not the only time glaciation has happened. 2 earlier periods of glaciation, both well known and well preserved in rock records, were evidently a lot less severe, but they did occur. The earliest known ice evidence, a relatively brief event revealed by the tellite deposits on ancient South African cratons, occurred about 2.9 billion years ago in the middle of the Archean Aeon. And a second longer cooling episode marked by extensive glacial deposits between about 2.4 to 2.2 billion years ago followed the breakup of the equatorial Kenorland supercontinent. And then for the next 1.4 billion years, almost a third of Earth's history, including the Boring Billion, no trace of any ice age has been found. Earth's climate seems to have remained in this remarkable balance of not being too hot or too cold, till obviously we reach our tipping point at roughly 740 million years ago. So that sort of concludes our discussion on what the Snowball Earth was, what was this whole period. And if you're liking this episode, make sure you follow, make sure you subscribe, and make sure you share it with anyone who would have a love for being very, very nerdy about history like you and I are. And for everyone else, thank you so much for listening. Thank you so much for following and staying with us. And I will see you in the next episode where we will discover the mystery of complex life forms and where do we do this whole Cambrian explosion thing. So yeah, thank you for listening and I will see you in the next episode. Bye bye.